So yeah, today we have the great pleasure to welcome Pierre Weiss to the 1W-Minds seminar. He has published a lot of interesting research within signal processing and image processing and also complex sensing. And today he's going to speak about blind image deblurring in microscopy. The floor is yours, Pierre.
Okay, thank you very much. Yeah, so I've decided to present this topic because I've been working on this for quite a long time. And today I will present an overview of what we did, say, in the last 10 years. But before starting on this, I wanted to show one picture. So I'm in Toulouse, and Toulouse is the place where we have the weather forecast in France, Météo France, and they have huge forward models to predict the climate. And here is a prediction that I made 5 years ago about the extreme temperatures we may see in France, so in 2100. And you see that this is the scenario where we would do nothing for climate, not change our habits in any ways. And you see that the temperatures grow, indecently, like to more than 50 degrees everywhere. And unfortunately, these temperatures is not something the human can sustain. Most forms of life just disappear with this. So, okay. With this slide, I want to thank the One World organizers. I think that this initiative is really excellent. And of course, it's an honor to be here. And okay, I hope that less people take the plane in the future. And okay, that we have more such events. So now I will go to science. I will stop with this and present where everything began for me. In fact, it began a few years before, but I will start here. So about 10 years ago, I was presented this image here. And this is an image of a tumor. It's something microscopical, and it was taken with what is called a light sheet microscope. And what we see here, those things here, those blobs are nuclei of the tumor, and biologists want to understand how tumors grow and so on. But the thing is, it's very difficult to penetrate in this sample. And we see here that the resolution is rather nice here in the middle, but here on the boundaries, it's very blurry. Okay. And so we've decided 10 years ago, okay, we should improve the quality of these images. And I would say that after 10 years of research, it's a complete failure. But today I'm here to say that we have some hope in the next 10 years. So we also tried to understand why it was so difficult to solve this problem. And for this, we generated this picture. So this picture is a kind of an indirect representation of the optical system. We had a cylinder of gel, and within this cylinder, we put some fluorescent microbits. And by looking at those microbits, so if the system was perfect, we should just see small dots. But here we see that we really have a huge blur patterns like this, and that they vary a lot in space. Okay, like here it's rather small, and here it's very, very large, meaning that we will average the image over a large portion of space, and it will result in a very significant blur. And the reason why we had so many troubles to invert these forward operators is because it's really something complicated that we don't even know. So this is another application I'm interested in. It's a super resolution microscopy, like single molecule localization microscopy. And here it's an image taken with what is called a wide field microscope. And the resolution is about 0.2 micrometers, which is already very good. And now with exactly the same microscope, what we are able to do is produce this image. Okay, so it's 3D, while before it was just 2-dimensional. And you see that the resolution is really much higher than before. And it's really the same microscope. So how did we do that? I will try to explain. It's by taking millions of pictures, actually, with the previous microscope. And this is one example of a picture that you could take with the previous microscope. So it's very small. It's 128 by 128, I think. And here, what you can see is just a few dots. In fact, a few point spread functions. And the idea is that since only a few molecules are activated in this slice, maybe you can try to find the location of this molecule with a subpixel accuracy. Then do this for a huge sequence of picture, like you have here in this sequence 1 million pictures. So at the end, you will get a few dots in space, but they are below the pixel resolution. And by stacking them, you can make an image And this image is what I presented before. Also, because the PSF varies in 3D space, you can assess the depth of the molecule from its shape. And this is how we reconstructed a 3D image. So right now, I think there are many very nice challenges in microscopy. And basically, what we want to do is go from microscopy to nanoscopy. In optics, this is really the challenge. A standard microscope, its resolution is limited to about 200 nanometers, which is already super good. I mean, you take 1 millimeter, you divide it by 5,000, and you get this. And now with technologies such as a single molecule localization microscopy, we can go nearly to 10 nanometers. This is really extreme. Only very few labs manage to do this. But there you take 1 millimeter and you divide it by 100,000, which is just super impressive. As a matter of comparison, you can take the atom size, which is 1 angstrom or 0.1 nanometer. And so it means that with this technology here, you can begin to see big molecules, which is already quite impressive. But the problem is that to have this machinery working, you really need super precise calibration and forward models, because you need to somewhat solve inverse problems. And for this, you need forward models. And this is what my talk will be about. And the current limit, I would say, is not really the diffraction anymore, but it's rather model mismatches, because if you have model mismatches, you will make like localization errors, which might be catastrophic, but also thermal agitation. And this, I won't go into the details of this, but your molecules are wobbling, and this creates blur also that is not related to optics. Okay, so the main objective today, we will be given a blurry image Y. We would like to solve, which is given as a product of A x bar plus B, where A is a forward operator and B is some noise. We would like to retrieve both A and x bar. Okay. And obviously, this is impossible in general, because there are plenty of triples A x bar B, which could give rise to a given Y. And so the first part of my talk will be dedicated to constructing families of operators, calligraphic A, to restrict the space of possible operators. We need this to be able to identify the problem. The second part of my talk will be to try answering this problem. Can we solve this problem if we have some prior knowledge on X bar? And how to handcraft methods. And the last part of my talk will be about deep learning, how to solve these problems with deep learning approaches. Okay, so I will start with some preliminaries in optics. So by looking at what I've just presented, you may think, okay, this is just a regular inverse problems, but it has some peculiarities that I want to discuss. So the main peculiarity is that specificity of this problem is that A can be expressed as a product of some sampling operator, SHA, and some blurring operator, H. And in my talk, so X bar here will be the clean image, and it belongs to some set calligraphic X. And depending on the place, it can be RM, L2, or the space of radon measures, because we may want to include the Dirac masses into the set that we consider. So H here is an operator from this set X to the space of continuous functions. And we want them to be continuous to be able to make pointwise evaluations, because we have a sampling operator, SHA. B is some noise. Typically, it will be Gaussian noise, white Gaussian noise. And this operator H here is a linear integral operator. So given an image X, the product HX is given by this integral, where K here is called the kernel of the operator. And we need this formalism to account for space variations of the operator. So by far in the literature, the most widespread model is the convolution. And in that case, we can say many interesting things. So in that case, K of ST is just a small k of S minus T. And then H is just a convolution. And there are many nice properties of this. First, it's a Fourier multiplier, meaning that you can diagonalize your operator with the Fourier transform. And something which is very important in optics is that by diffraction, the kernels K here are band limited, meaning that the support of the Fourier transform of K is bounded, as in a compact set. And so there are some good news associated to this, which says that if we sample sufficiently finely our signal, we will have no loss of information. But the very bad news is that also when you convolve by K, you lose the high frequency information completely. And it's kind of an irreversible loss of information. And this is what we will need to fight against to get our resolution again. Okay. The second problem with this simple convolution model is an identifiability issue. So assume that you observe y equal k convolved with x. Then there are an infinity of couples k prime x prime such that y equal k prime x prime. In fact, it suffices to convolve k with some filter g and x with some filter g minus 1, which is defined in the Fourier transform as the inverse of the Fourier transform of g, and you get this identity here. Okay, so basically there is no identifiability at all for this problem, and it's hopeless to solve a blind inverse problem if you don't have prior information. Okay, one nice way to say that is that the bilinear mapping is not injective. Okay, so now I will turn to trying to restrict the space of operators, because if we have two large spaces, we have no chance of solving the blind inverse problems. And I will tell what we can do in optics. So the first thing we can do is to rely on physics. And here we have nice theory of Maxwell, Fresnel, Fraunhofer, which tell us that the point spread function is not anything. In fact, it's at least if you look at the focal plane, it can be defined as the Fourier transform of the pupil function. So the pupil function is so usually in a, say, camera, you have an aperture, which is circular, for instance, and the PSF of your optical system will only depend on the state of the light in the circular aperture. Basically, the phase and the amplitude at every point of this circular aperture will allow you to estimate the point spread function. And so, according to this theory, the 3D point spread function is given by the squared modulus of the Fourier transform of the pupil function. And then if you want to go to other planes, you need to add some propagation because your wave propagates in space. And there is an extra propagating term here, but which is quite easy. So with a computer, it's very easy to synthesize point spread functions with this theory. And the nice thing is that if you have a circular aperture, what you can do is try to expand this pupil function in the basis of Zernike polynomials, which are orthogonal polynomials on the disk. So here there is a representation of them. So for instance, you can truncate your expansion in this basis of polynomials and say that the pupil is approximately equal to this. And here we just expanded the phase of the pupil function in this basis, because usually the modulus in the pupil plane is about constant. Okay. And with this, you can generate quite complicated point spread functions like these ones. Okay. And here it's interesting because you see that it's quite a rich description, and this was with only 7 coefficients here. Okay. With 7, you can really create quite large variety of realistic blurs. So it's really cool, but it's still problematic because it's space invariant, and also it's very highly nonlinear with respect to gamma. So we may want to have other models which would be able to take the space variations into account and also be linear. And so for this, we've asked a colleague of ours, Thomas Mangerin, to generate those images. So what you see here, it's an image with a wide field microscope, and we've put some microbeads inside the cover slide. And what you see is an indirect representation of an operator. You see the point spread function of the operator scattered in space here. And then, so somehow with this information, you have some hope of reconstructing your operator by some interpolation technique. But what we can do is vary the imaging conditions. So what we did here is change the focal plane, change the location of the beads, change the temperature in the room, because it will induce changes of refractive indices. And then you get a more, you get some information about the whole diversity of the optical response your microscope can have. Okay. And what the next part of my talk, I will try to explain how from this sequence of images we can try to construct a low-dimensional family of operators mimicking all the possible states of the microscope. So I will not enter into the mathematical details and just explain with the hands. So here is one picture. So from this picture, what we can do is try to make a rough detection of the point spread functions. Okay, they are in red here. Then from this, we can try to remove the background locally because there is usually some background noise. And when this is done, we can try to find the center of the point spread function with a subpixel accuracy. And I will say how we do that later. We have a nice theory for this. Okay, then when they are all registered, these images, we can do principal component analysis plus some z-test to avoid outliers in the estimate, and keep the components which are the most meaningful. For instance, here we keep 3 components, and these 3 components are enough to express all the point spread functions in the field of view of one operator, given one condition. Okay. So once we have them, what we can do, once we have this eigen PSF basis, what we can do is project every PSF that we found before in this basis. And so we get like 3 coefficients here at different points in space. And from this, we can construct maps. We can make some kind of interpolation of the coefficients of the PSF. For instance, with thin plate approximations. In practice, it's a bit more complicated. We add some physics into this process. But at the end, given these continuous maps, it's very nice because, for instance, I take this point. At this point, I have 3 coefficients. And from these 3 coefficients, I can reconstruct the PSF at a given location in space where I didn't observe a PSF. Okay. And so this here, the combination of these maps, interpolation maps, and the eigen PSF gives a complete representation of the system since we have the PSF at every point in space. So we do this for all of the image in the sequence. And somehow at the end, what we get is, we can say that we have low rank approximations of our operators somehow. Okay, for every image in the sequence, we have a low rank approximation of the operator. And then what we do is what is called a higher order singular value decomposition to estimate a single basis EN1 and FN2, which would be able to simultaneously, to jointly approximate all the operators that we've seen before. Okay. So at the end of this process, which is a bit technical, but okay, it's okay. We have a basis EN1 of what we call eigen PSF, which is basically something that will allow to express any PSF of any operator within any point in the field of view. And eigenspace variations, which encode the variations of these coefficients in space. And now we have a linear parametrization of an operator family, h of gamma multiplied by x. We can say that it's this double sum of gamma n1, gamma n2, where we first multiply x by some eigenspace variation fn2, and we convolve the result with the eigen PSF basis. And so here is what we can do at the end. So for instance, here we've synthesized operators. These are not operators that we've seen. And here I just represent PSF on a regular grid over, and you can see that we have operators that vary in space with rather complicated point spread functions, and they represent all the operators that we've seen until now. Okay, so well, it's not working. Okay, here we have a low-dimensional subspace of operators able to reproduce all the possible states of the microscope. Okay, so for this we are currently developing a plugin under Fiji, because this is used for people in optics or biology, which is called eigen PSF extractor. It's already available if you ask for it. And we have a theory. We've shown that this procedure of estimation is minimax optimal to estimate the family. Okay, so right now I hope I've convinced you that we can consider more restrictive model that I've described before. We can say that Y is A of gamma bar X bar, where gamma bar is some parameter. And A here is a parameterized operator. So we have gamma bar here lives in Rn, and A of gamma bar is a linear map from X to Rm. And gamma bar is an unknown parameter. So now the problem is not to find A, but it's to find gamma bar and X bar. And it's already a much simpler problem than what we had in the first slide. And N is typically small. So in the application I've shown, it's ranges between 5 and 100. So now I will turn to what we can do. When can we identify the operator and how can we identify it? So one thing we worked a lot with is the case of isolated sources. So here is a picture. It's synthetic, but it's kind of realistic, where we have observed a few point spread function in space with some additive noise. And from this, we would like to find the location of the molecules, say, and the operators as well. So the algorithm we proposed is find only the isolated sources, and from this, try to estimate the operator. Okay, and once we have the operator, we can use any algorithm that already exists, for instance, total variation minimization, to disentangle the clusters of molecules and make super resolution in the hard part. So the first part will be to just locate the isolated molecules, which usually happen in microscopy, and then from reconstruct the operator and then disentangle the clusters. Okay. So for this, we need to say what is an isolated source, how to localize it, is it robust to noise, and is this information enough to recover the operator stably? And well, there are positive answers to all of this, and I will try to explain how we can do this. So we assume that we are given a collection of regularizing operators, AN, which are mappings from the space of radon measures to the space of continuous functions vanishing at infinity. And we assume that our forward operators depends linearly on gamma, so it's just a linear combinations of these elementary operators AN. And then, okay, so this is the family of forward models. And then, given a measure mu in the space of radon measures and a collection of linear R forms, we assume that we observe Ym, which is nu m applied to A of gamma mu plus Bn. So this is the observation model. So for instance, if nu m is just a Dirac mass at some sampling location, we get the standard sampling model. But this model is more general. Now, to localize the sources, what we can try to do is, okay, we fix a rough region where we know that a molecule should be. Usually, this is not too hard, so I will call this region in space calligraphic D. And what we can try to do is find a point X in this space D and a parameter gamma, such that A of gamma applied to delta X, so the image of a Dirac mass at X with parameter gamma is close to Y. And in fact, to analyze whether this works, we need to introduce this mapping, which goes from RD, so this is the space of molecule positions, to Rm times n, which is defined in this way. And basically, the meaning of this mapping is that if you evaluate this mapping at X, you get a matrix. And if you multiply this matrix by gamma, you get the image of a Dirac mass at X with an operator gamma. So this is this mapping allows to synthesize images of PSFs at any point in space with any operator parameterization. So introducing this mapping, what we can show is that solving this problem is equivalent to this one. So we let calligraphic R of X be the range of E of X. And what we want to do is, so we here in this problem, we discarded the dependency on gamma here. And what we want to do is find the range in space, which captures most of the information of the observed image, which is quite natural. Okay, so, and this can be solved, say, with the Newton method, for instance. And now I will try to explain how well this works. So for this, I've generated this picture. So this is an array pattern. You don't see it in this heat map there, but if you change the color map, you can see that it oscillates. Okay. So now what we can do is launch the previous algorithm in the noiseless setting. So here I assume that the norm of the noise divided by the norm of the signal is 0. And there, okay, I get a perfect recovery of the location of the molecule. That's natural. Then I add some noise. Already the norm of the noise is 10 times larger than the norm of the signal. So we still get something near perfect. We increase it, it's still perfect. We increase it, still perfect. And here it's really quite impressive. Now, like the human eye could say that the molecule is here, and the result is still perfect. And still perfect. Okay, here it looks kind of impossible to do it. And finally, here at 45, okay, it breaks down. So we wanted to explain this phenomenon. So for this, first, we can make an experiment and measure the % of success. So if we do different noise realization, we can trace a phase transition graph where we look at the percentage of success with respect to the noise level, norm of B over norm of Y. And we see that until like 30, we get always a perfect recovery of the molecule position. And here success means that the position of the molecule is less than 0.5 pixels away from the true locations, meaning that we have a super resolution effect. And then it goes down slowly to 0. So we wanted to explain this, and we came up with a theory which involves this quantity here, this function phi. So I will try to explain it. So you have two ranges. What matters in the problem is the range of your operator, R of x. Okay, and so if at two distinct points x and x prime you have two different ranges, then there is no way you can identify the molecule position, because basically whether your molecule is here or here, it could give rise to the same image. So we want the product between those two projectors to decay. Okay. And so we need to control it. It will be 1 if x equals x prime, because then this is just the two norm of a projection mapping. And we let phi denote the largest non-decreasing function, so we want phi to increase, satisfying this inequality here, okay, which is quite natural. Now, assume that mu bar is a Dirac mass at x bar, that you have this observation model, and that the norm of the noise is less than theta times the norm of y, where theta is less than 0.225 for some reason. Then what we could prove is that x hat minus x bar is less than the reciprocal function phi minus 1 applied to 2 theta squared plus 4 theta. So this is quite nice, because we already see that the norm of the noise can be of the order of the signal level, and we still get some recovery, some location precision. But it does not explain what we observe, because before theta was like 40 and it was still working. So to go there, we need to account for the fact that B is not an arbitrary perturbation, but it's random noise. So we tried to devise a theory for this. I will just give an informal result there. And what we've proved is that if B is some normal noise, white Gaussian noise with standard deviation sigma, and that the AN are convolutions with normalized and band-limited kernels, then we will get a subpixel localization with high probability, given that the standard deviation is less than the norm of the signal divided by the square root of the log of measurements, number of measurements. And this is quite natural, because if you observe many measurements, the probability that you have a false detection increases, but it decreases very, very slowly, like square root of log m. Okay. And so this really explains the favorable numerical behavior. We've shown that asymptotically, when the noise goes to 0, this also, we get back the Cramer-Rao lower bound, and I think that this is quite a nice analysis. Okay. And basically, this is the algorithms we've used to localize the molecules with a subpixel accuracy in the previous slides. And now, so at this stage, I've proven that we could retrieve the molecules location with a subpixel accuracy, but now the problem is not over. We have another theorem, which is still informal here, that now if we observe some measure mu bar, and okay, which is this, it's a discrete measure, and that the distance between the molecules are larger than some threshold, which I don't describe here, then we can retrieve, we can make accurate estimates x hat p of the x bar p, and then we can try to solve this bilinear problem to retrieve the operator parameterization. Now we have fixed the molecule localization, we just don't know the weights and the operator parameterization, so we can solve this problem, and we can show that gamma hat is a stable estimate of gamma bar. Okay, and so we've solved the blind inverse problem, given that we had isolated sources. Okay, so it's very nice, but it's just points, and points are not very impressive. So we've tried to do, well, here it's not us, maybe it's even Felix, so nice, Felix. So it's the first paper of Felix Cramer from Google Scholar. So assume now that instead of points, you see edges in your image. And that you have a convolution model. You observe y equal k convolved with x bar. can we do something in that case? The answer is yes, because now if you evaluate the convolution product between x, which is the 0, 1 function here, and h, and you evaluate it at this point, you get the integral of h over this part of the disk. Now, if you evaluate the convolution product, say, just slightly on the left, you evaluate the integral of h, but over a smaller disk. Okay? What this means is that if you compute the derivative of the profile of your function normal to the edge, you will evaluate the integral of h over a line here, and this is nothing but the radon transform of your point spread function, okay, in one given direction. So now if your image contains edges in different directions, well, you get a full view of your radon transform, and somehow it's something we know we can invert, okay? And this idea is basically, I think, the state of the art for handcrafted methods. Usually it's not presented in this way, but I really think that this is what is behind why it works. So the idea is to first identify the edges and their direction from the blurry image Y. Once you know this, you can compute the normal derivative. Once you have the normal derivative, somehow you have the radon transform of your signal, so you can try to invert it and pray. Because it's a very complicated process, you had to find the edges and their direction just from the blurry image. It's not easy. And basically, this is really what works the best. For instance, these papers are very, very popular. But our experience is that it doesn't work so well. It works in some test cases, but most of the time it doesn't work so well. Okay, another thing I like a lot is assume that you just have a natural image, and the natural image has some scale invariance property, meaning that its Fourier, the modulus of its Fourier transform decays like this. Okay. Then under this model, if you apply the Fourier transform, you compute the Fourier transform of your blurry image and you multiply it by this frequency omega, then you see that you get the norm of the modulus of the Fourier transform of your signal. And somehow under the scale invariance model, you see that the kernel estimation is kind of equivalent to a phase retrieval problem. And this leads to other families of algorithms, which are also very nice, which work quite well in practice here. Okay, so what I've said till now is that we can devise identification theories and algorithms when we have isolated sources, images with sharp edges, or natural images with a typical frequency contents, okay? So as a conclusion, we have many cues in the images which are available for blur identifications. But it's not easy to use them because usually they are all mixed up. And I think that this is a typical case where I think deep learning can really change the game. And this is the last part of my talk. We will try to have an algorithm learn for us how to use these different cues to identify the blur. So we were very, very excited about what we did. And then we did some bibliography and we realized that there were about 100 papers on this topic. But okay, our approach is still nice and I will present it. So we designed this architecture here. And okay, it's a nice picture. And it's there are two networks here. The first one is what we call an identification network. So given a blurry image, it's a kind of encoder structure. And its aim will be to find the parameter of our operator, because we know that we have low-dimensional parameterization of our operator. Now, once it's estimated, we have an estimate of the forward operator, so we can feed this estimate to a second neural network and also the blurry image, and use what we call a deblurring network. And now I will describe these architectures. So, this is the identification network. It's a residual network. And the way we train it is a bit original. So we assume that we have collections of signals. In my experiments, I used the MS-COCO database. And we just pick these images uniformly at random. So this is very standard. Now, what is a bit tricky here is to sample the operators. We need to sample the operators at random. And for this, we need to devise some distribution on the space of operators, capital gamma. Then we also need to add some noise. And for this, we just assume that we had white Gaussian noise. And we varied the standard deviation of the noise.
Je viens, ouais, j'arrive, c'est bon.
Okay. So we vary the standard deviation of the noise to account for different noise levels. And now the identification network depends on some weights W that we need to train. And it's a mapping which goes from Rn, so the blurry image basically, to Rn, the space of parameters. And so to train the identification networks, so we will draw images at random, noise at random, parameters at random, and we will just try our identification network. We feed it with the blurry image, and we want this to be as close as possible to gamma n. Okay, and we solve this with the Adam optimizers, like everyone. So how to sample the operator set? So here it's a bit tricky, and we had to design what is called maximin solvers. So we assume that gamma is compact, capital gamma is compact, which is the case in most applications. Otherwise, basically, it's very hard to sample a non-compact set. And what we will try to solve, we will try to find the collections of operator parameters, gamma k, which are the solution of this problem here. And this problem is basically we want to spread as much as possible the gamma k's inside the compact set gamma. So we want the minimal distance between pairs of parameters, gamma k prime, to be as large as possible. Okay. So this is what we call maximin solver. So for some reason, which I didn't have time to describe, usually our parameters live in a convex set. So for instance, we have some extreme points here, and we would like to sample as well as possible this compact set here, which is the convexel of those 4 red dots. If we are a bit naive and that we just sample uniformly over the simplex and that we do random convex combinations of these extreme points, we get this. Now, if we use our maximin solver, we get this, which is much more even and much more spread. So somehow solving this maximin problem is a good way to have a minimax estimator for our operators. Okay, and now some results. So I think I picked these pictures, we have many more. And what I want to say is that it's working extremely well. I was super impressed by it. So here we have an image of a bird in front of a forest. And it was convolved with this kernel, which comes from diffraction theory. So here it's a physics-based model, and we use this very nonlinear mapping to synthesize this blur kernel. So we get this blurry image. It's also noisy. And we feed this image to the identification network, and it gives us this blur, which is near perfect. Okay. Now we feed this image, it gives us this blur. We feed this image, it gives us this blur. And this is super impressive because like here you have nearly no contents. It's a white sofa in front of a white background, and we get a near perfect recovery. Here, why is it impressive? It's because this image, okay, it's rather sharp in the foreground, but it's very blurry in the background. And the identification network is able to disentangle the defocus blur from the one related to the diffraction blur that we've synthesized. And okay, so this is very impressive to me. And in fact, the things work very well. It's super robust to noise. And okay, we are super happy with these results. Okay. Now about the deblurring network. So I don't want to go too much into the details of this, but this is an unrolled architecture. And what we've done, so to explain this for people not familiar, a good way to explain them is to go back to convex optimization. So for like 20 years, people have been trying to solve this kind of problems as fast as possible, where you have a data fitting term here, f, which depends on the forward operator a, x, plus g of x, and this here is a regularization parameter. One algorithm you can use to solve this type of problem is called Douglas-Rashford, and it's quite easy to interpret. In fact, at one stage here, you will basically try to invert your operator, and at the other stage here, you will try to denoise the image that was inverted, and you iterate. And after some iterations, you get a convergence sequence to this problem if f and g are convex. And really what matters here is the interpretation between you make an approximate inverse of your operator and then you denoise it. Okay, it's also the plug and play philosophy for those who know this. So the idea of the unrolled network is to replace this handcrafted prior prox of G by a neural network, which I call a proximal neural network, explaining the PN here. Okay. So the deblurring network architecture is a mapping which takes a parameter W. These are the weights to be trained, an operator A, and a noise level sigma. This is quite important because we want also this deblurring network to accommodate to different noise levels. And our weights can be decomposed as T weights, because we will do capital T iterations of the previous sequence. So at every iteration, we will have a different proximal neural network. In our case, it's a state-of-the-art denoising convolutional neural network. And the deblurring network is this sequence. So it's exactly the same as the previous one. We start from the blurry image, we denoise it, then we invert the operator, and so on. Okay. And at the end, to train this network, so we need to train all those weights, which are basically the weights of the denoisers, the proximal neural networks. What we do is the interesting part is that we don't give the exact operator. With the exact operator here, we would have gamma n. We feed it the estimate of the forward operator given by the identification network, which was trained previously. So this way, somehow this neural network learns how to handle model mismatches, the mistakes we may have done in the estimate of the forward operator. Okay, so now some results. So here is a picture from the MS COCO database. Here is the blurry one with this diffraction blur here. And here is the estimate. So both the blur estimate and the estimate of the sharp image. Okay. So you can see that the estimate of the blur is not perfect, but it's also already very good. We lost like this ear here of the pattern. And but we gain really a lot of resolution. For instance, here it looked hopeless to find this texture, or here on the wall this texture, and you can look and we recovered the texture. And with standard method, it's nearly impossible, I would say, to do this. So in comparison, this would be a handcrafted method, L0. So you see that the estimate is quite good, but it's reversed. I don't know why. Okay. It's symmetrized, and we also find the texture a bit. So here I must say it's without any noise, so it's quite easy. And there it's the Goldstein-Fatal method based on the power spectrum ID, and it works also relatively nicely. You still get a sharpening of the image and a rather nice estimation, even though it's flipped. And this is NAFNet, which is the state-of-the-art network from GoPro, but it was not trained with these models, but it's really not able to handle this. Now, if we add quite a lot of noise, what happens? So this is the estimate with our operator. So first, you see that the estimate of the model is nearly the same as before. It's super stable to noise. And now, okay, we are not able to reconstruct the textures here or here, but still, the details are much better restored. In comparison, this would be the handcrafted L0. So I think you would agree that this is much better. And this would be the Goldstein-Fatal method, which has some deep learning involved. And this is NAFNet. Okay, just blows up completely. It even invents color. So this is another picture. So the blur, no noise. So this is the result with our estimate. Again, the estimate of the blur is not perfect, but it's quite good. This would be the handcrafted L0, which is kind of state-of-the-art for the humans. And this would be Goldstein-Fatal. This is the state-of-the-art for NAFNet, so it just doesn't work. And this is with a lot of noise. So here the challenge is to try to recognize what is written on the bus. And okay, we can recognize Metro Centro here. And I would say that it was not, you would probably not be able to do it just from this. And here you have more chances of doing this. So there is really a gain of resolution here. This would be the L0 method, which is not good, and the Goldstein-Fatal method, not good. Okay, enough now. Okay, now we can also try this on biological images. So here it's still synthetic. It suffers from a space-varying blur here, and this is the result of our method. So it's really good. You can recover nice textures that looked completely lost beforehand. And this would be a total variation solver for comparison, but where we know the exact operator. Here we assume that we feed the solver the exact operator, while here it was estimated by the method. And still, this blind method works much better than the total variation method. For instance, look at this nuclei here. you have much better details. Okay, so it's the end of my talk. So I have a spark of hope, not for climate, but for blind deblurring in the last year. There are many nice open theoretical questions. So what is identifiable for advanced models? Estimate stability constant, because this is currently lacking in the literature. As for deep learning, we want to stabilize the operators to family mismatches. We are currently working quite a lot on this, because maybe the operator does not live perfectly in the family that we've synthesized. And also, what is the best achievable performance to know if we need to train models for hours or if we can stop there. And we have we are working in close collaboration with biologists, and we have many applications in super resolution for different microscopes. And we are also trying to reduce our carbon footprint. So I've tried to assess how many watts we've spent doing this. And it turns out that we had like 2 megawatt hours, which is about 150 liters of oil, which is quite a lot. So this was about 1 year for 3 people who also needed to get trained with this. But still, it would be very good if we could reduce this. Okay. So this is the end of my talk. I want to thank my collaborators. So by order of appearance, Paul Escorn, Jérémy Bigot, Valentin Nebarno, Thomas Manja, Emmanuel Soubiès, Daniel Sage, and Nathanael Munier. And here are 8 references about this work, because it's been a long work. Okay. Thank you very much.
Thank you very much, Pierre, for the nice talk. Are there questions from the audience? If not, maybe I can start with one question. So still, even in the deep learning framework, you are assuming that you have this linear family of operators. Do you think that it would make sense to try to go beyond that, to have some non-linearity within that model?
So it's not entirely true. Here I've shown both linear and non-linear parameterization. Like all of this is non-linear because we've synthesized the point spread functions with the Fresnel diffraction theory. So it already works with non-linearities. I think that it would be very nice indeed to estimate families of operators in a non-linear fashion. For instance, with, I don't know, GANs or whatever. And we are not there yet. But I think this is a very nice research opportunity. Not so many people. In fact, I found nearly no one trying to estimate families of operators. Usually you try to estimate one operator and it's already very complicated. Here you need to find a family or a manifold of operators. And I think this is a very nice research field with not so many people involved. So you should go there.
Are there other questions from the audience?
I still make some advertising.
So, as you know very well from reading a thesis jointly with me, there's an ongoing discussion about robustness of deep learning methods.
Mm-hmm.
So, what is your impression about the stuff that you're doing here? Do you expect that that things be relatively robust, or will the classical methods be somewhat more robust to perturbations?
Yeah, it's a nice question, and we are working quite intensively on this. So here, the training is different from what is usually done with neural networks, in that we don't train the network on one operator, but on a family of operators. And so we could expect a significant loss of performance because our network is not adapted to just one single operator, but to a family. And so we in a recent work that I didn't present, we have assessed the loss of quality induced by training on a family rather than a single operator, and it's negligible. But the gains in doing this are kind of huge because we've shown that it was working well uniformly on all the operators on the family, and that it could even extrapolate to some extent beyond the family. And now we are rather convinced that if you train your neural network well, and here we really do something different from what is done currently in the literature, because we train on a family with different noise levels, we have many different ingredients. The method is super robust, and in any cases, much better than handcrafted methods, at least for natural images. I mean, images with complicated contents. It's much better, much more robust, and much more prone to solving blind inverse problems.
So would you, I mean, would you say then that sort of having a more general training approach as compared to a more problem-specific approach helps increase robustness?
Yeah, so there is a trade-off somewhat, because like on the other extreme of the spectrum, you could use the plug-and-play approach,
yeah,
where you would train this denoising network just to remove Gaussian noise, white Gaussian noise. This is a plug-and-play approach, and it works really well, but there is still a 1 decibel, 2 decibel drops compared to this. So somewhat a universal approach that would be trained on all possible forward operators would not work so well. So you need to restrict somewhat the family of operators to something which is realistic for your system, but not too much, because otherwise you will begin to see the performance drop. So there is a kind of trade-off, I think, and which is a nice also research avenue.
Okay, thank you.
More questions? If not, then maybe we should end the seminar at this point. Thank you very much, Pierre, for the nice
thank you very much.
Thank you, and also thank you for digging out my very old paper.
Yeah, no, but it was very nice, actually, your first paper. Is it published, by the way?
No, it was okay. It was like a graduate student, like they had this graduate student, I think.
Okay, project. Okay, it's nearly your most cited work. So congrats. No,
yeah. I think that they were also. I mean, the mentor of the project at the time in 2006 was Brent Wahlberg, and I think I met him also at some conferences later, and he was saying he was also impressed that this was just sort of a write-up and sort of a compilation of literature and a comparison, and he was so surprised how this is also one of his most cited papers.
Okay,
could have been up, but we just didn't.
Okay, well, anyway, congrats for this nice one. Okay, well, I guess I can leave, or yeah.